Next topic, the other kind of popular shift register counter. The name is Johnson counter or twisted ring counter. Okay, other names also I have already written. Okay, I have already shown you. What's the difference? In the case of ring counter, the arrangement was like in a serial in serial out shift register itself. So the out and like a feedback output of the last flip flop is fed back to the input. Okay, but in the case of ring counter or in the case of twisted ring counter or Johnson counter, the output of the inverted the inverted output of the last flip flop is fed back to the first case. Okay, the inverter output, that is we have 4 flip-flops and the inverter output, we have 2 outputs, right? Inverter output, that Q4 and Q4 bar, the result of the Q4 bar is taken and fed back to the D input. Okay, we'll go for the description. This counter is obtained from a serial in serial out shift register by providing feedback from the inverted output of the last flip-flop to the D input of the first flip-flop. The Q output of each stage is connected to the D input of the next stage, as in the case of a serial in serial out shift register. But the Q bar output next we have the second kind of shift register counter. The name is Johnson counter or twisted ring counter. Okay. What's the specialty of ring counter? We have already realized or understood how it works, right? It works like a serial in serial out shift register, and also the output of the last flip flop, that is Q4 in the last case in the figure. Q4 is fed back to the D1 input. Okay, so it forms a cycle. We already know the concept. But what's the difference between a ring counter and a twisted ring counter? In the case of ring counter, we took the what we call the Q input of the last flip flop, but Q output of the last flip flop. But in the case of twisted ring counter or Johnson counter, what we take is we take the inverted output of the last flip flop. That is, we have 4 flip flops, FF1, FF2, FF3 and FF4, and the output of the last flip flop is Q4, right? So we have the inverted output means Q4 bar. That output will be taken and fed back to the D input of the first flip flop. Clear? So how it works and what are the things that we need to note here? The counter is obtained from this counter is obtained from a serial in serial out shift register by providing feedback from the inverted output of the last flip flop to the D input of the first flip flop. Okay, inverted output of the last flip flop to the D input of the first flip flop. The Q output of each stage is connected to the D input of the next stage, as in every serial in serial out shift register. But the Q bar output of the last stage is connected to the D input of the first stage. Therefore, the name twisted ring counter. This feedback arrangement produces a unique sequence of states. Okay, this is a concept. We will also go for the diagram and the state diagram and logic diagram. Okay, please go through. This is the logic diagram of 4-bit Johnson counter using D flip flop, and this is for JK flip flop. Okay, so what's the difference? What I told, I have already given the explanation regarding this. The only one change when compared to ring counter is here we need to take the inverted output. Okay, it may not be so clear. It's D1, Q1, Q1 bar and D2, Q2, Q2 bar likewise. Okay, so we take the last flip flop output, the inverted output, and feed that back to D1. Okay, that's the difference. That's the case with what we call D flip flop. Sorry, Johnson counter using D flip flop. Okay, and in the case of JK flip flop, what we need to do is we take the inverter output and feed back to J1 and take the actual output and give such a connection back to K1. Okay, please go through. this is the state diagram and this is the table. Okay, sequence table. So how does it work? Okay, as I told, we have 4 flip-flops for this case. Okay, we have 4 flip-flops, and initially let this flip-flop, we already have the figure. Okay, please compare with that. Okay, so all those flip-flops, flip-flops are reset to 0. So all those values will be 0. After each clock pulse, what happens is, we have now Q4, that's the, just imagine, okay, the Q4 which is at the rightmost side, Q4 bar will be 1. Okay, so what we do is that after each clock pulse, that 1 will be shifted to this place. Which one? D1. So it becomes 1 0 0 0. Okay, and after that, this is the flip-flop output, right? So this is now Q4. Q4 bar will be 1. So it becomes 1 and it will be fed back to Q1, when D1. It becomes 1 1 0 0. So in each case, Q1 is shifted to Q2, Q2 is shifted to Q3, Q3 is shifted to Q4, and Q4 bar is shifted to Q1. That is the operation. Okay. Similarly, we get 1 1 0 0, 1 1 1 0, 1 1 1 1, 1 1 1 0, 1 1 1 1. Next is 1 inverted, means it becomes 0, it is fed back and these are shifted. So 0 1 1 1, 0 0 1 1, 0 0 0 1, 0 0 0 0. Okay, and after that, again, next clock pulse means this becomes 1. So this is fed back 1 0 0 0. That is the same result. Okay, so we should say that after every 8 clock pulse, this is the initial condition, and after 8 clock pulse, it cycles, it forms a cycle. So what is the specialty, or what at the first glance we can understand that in the case of ring counter, when there was 4 flip-flops, there was only 4 states. Okay, but in the case of Johnson counter, when we have 4 flip-flops, we have 8 states, which means for n flip-flops in the case of Johnson counter, we can form 2n number of states. Okay, and based on this, we have what we call the state diagram as well. We can start from any position. If 0 0 0 0, you can start from here also, no issues, but we need to follow the pattern. Okay, here we have 0 0 0 0, 1 0 0 0, 1 1 0 0, 1 1 0 0, 1 1 1 0, 1 1 1 1, 0 1 1 1, 0 0 1 1, 0 0 0 1, and after that it again 0 0 0 0. Please go through. This is what I told you. The first point is an n bit or n flip-flop Johnson counter can have 2n unique states and can count up to 2n pulses. So it is a mode 2n counter. Okay, and also it is more economical than the normal ring counter, but less economical than the ripple counter. This is the timing sequence or timing diagram. Okay, we mark 0 1 2 3 4 5 6 7 8 9, that is in total 10 pulses. Okay, and like I said, if we have the sequence diagram that we have already sequence table that we have already constructed, if we have it with us, it's very easy. Okay, initially during clock pulse 0 means 0 0 0 0. Now we have 1, this is high, 1 0, this is deep. Okay, 1 0 0 0, 1 1 0 0, 1 1 1 0, 1 1 1 1. After 1 1 1, it's 0 1 1 1, 0 0 1 1, 0 0 0 1, 0 0 0 0. 0 0 0 0 means in the 8 clock pulse, right? Just let me look. Yeah, and after that 9 clock pulse, 1 0 0 0. It's very easy, just based on the sequential circuit, sequence diagram. Okay, please go through.